This is about improving the code quality in Arch directory in Linux and in making architecture developers talk to each other at least once a year. Several technical announcements notes before we start. There is a live chat. Everybody is welcome to ask questions and say anything they'd like to. We do respect anti-harassment and so on, and etc. Everything is recorded and the chat will be later available online. If you'd like to chime in and ask a question, please switch on your camera so we'll see that there is a question ongoing. For the speakers, usually there are lots of questions in the chat, so do some pauses and look at the chat questions and try to respond to them as well. Maybe somebody will read out the questions to ease the process. And now to you, Arndt.
Yeah, thank you. One more thing, we have these in case one of the speakers is like at the end of the talk. We'll let you know when it's at the end. Yes, let me just switch the presentation here. My first session is about planning code obsolescence. So I have removed a lot of code in the past. I have removed something like 8 architectures, and Mike has removed another one very recently. But it's always very hard to find out what we should remove or we should not remove. So what I want to get to here is find some policy about documenting the state of code so that it becomes easier for everybody to understand whether something is actually used by anybody or if it can be removed right away. And like in the past, we have kept code around for 10 years or longer that obviously never had any users. And at the same time, we've sometimes removed code that had users. And those are both things that we want to avoid. So to define what I mean about the difference, there's obsolete hardware, which includes a lot of things that are just not made anymore because they have been replaced with something that's newer, cheaper, and better in any possible way. But people are still using it, or they may be still using it. We might not know. There's also obsolete code, which might be for hardware that's still under production, but all the users that are remaining are running some older kernel and are never going to upgrade. And at that point, the code can and should be removed in general. So what I'm proposing is that we find a way somewhere to document configuration symbols that are for obsolete hardware support and that are still in use, and then we document why they are in use, how long we expect them to be in use, and what we might possibly gain if they are removed, like other things that depend on them that we might also want to remove. So some categories that this might impact, there's a whole lot of hobbyist platforms. There's whole architectures that have no commercial value anymore, but that are actually used by a group of people. And in a lot of cases, we don't know what they are. Like if there's, I don't know if there's anybody using a Sun 3 workstation from 1986. There might be, but probably there isn't. It would be good to document those. And then there's a lot of platforms that have very specific uses for very few users, but they absolutely need them, and they absolutely still need to update their kernels. Those are usually like embedded systems with very strict rules about code quality, where they do have to upgrade their kernels. And then we might go even further to systems that that will become obsolete in the future. Like I've actually got to talk about this tomorrow at the Kernel Summit, where one thing I show is that big endian platforms have declined something like 90% in the last 10 years, and I expect this to continue. At some point in 10 years, maybe 20 years, big endian might go away. Same for 32-bit systems. They are still used a lot these days, but eventually they will go away. And the question is when. So we keep hearing that 32-bit is all obsolete, nobody's using it. That's obviously not true. So we should document why is it used and when do we expect the last one to go away. And then I'm actually at my last slide here. And there's a question like, where do you document these? Like, do we create a new file in documentation? Do we put this into the kconfig files in some new format? We put it into the maintainers file, the wiki, or somewhere else? Let me just start a poll here. Oh, everybody was ready, and now, oh, fine. There's only 5 options now. There were 6 options earlier when I tried this out. Now there's only 5. There we go.
I'll help you.
Thank you. For some reason, you seem to be seeing other options.
I see 6 options. I don't know.
Yep.
And we nearly half voted.
Okay. Let us see.
I don't know. Can I? Waiting for poll. Anybody wants to press a button or something? Let's wait for a couple of seconds, maybe. Okay. Let's say we had 53 voters out of 80 people, and I'll give the presenter back to you.
Thank you. Right, that is a fairly clear vote on having this in the documentation directory, possibly also tying into the kconfig system, I think. And that's totally possible. Like, we could have something in documentation where we reference kconfig symbols and something like that. So any comments? Anybody who wants to speak up? Because that's all I had for like the presentation part of this discussion session. Check the chat here. So there was some discussion on the chat about, oh, yes, John.
Well, I can start by asking, how is this going to be different from the old feature removal.txt file that we used to have that we decided to get rid of?
Well, this wouldn't be a schedule in the sense that we decide upfront that we will remove something. It would more be something like, let's keep this for at least this long. That's at least my idea. And then people can update it when they are still using it. And I would think there should be a fairly low barrier to updating it. Like, you just send a patch saying, I'm still using it. I've booted this system this month. If we recall at the time when it was still used. We shouldn't assume that everything there will be removed. It's more like documenting both sides of the picture.
My experience is the barrier to updating documentation is always high.
Do you plan to see like config obsolete? Like, we have config expert, but other config obsolete in there?
Well, there's the question about how obsolete, right? Like, we have obsolete hardware and obsolete code. And I think the config obsolete was a little bit a mix of both, right? It was mostly used for obsolete hardware, which probably applies to something like 80% of the drivers we have. But that doesn't mean they're not used anymore. I was thinking more something like config steampunk for the really old stuff. Like we would have a dependency on a symbol that we make up for stuff that has no useful purpose, but is actually really fun to use, and people are really fond of their systems that they still have. And possibly some other systems, symbols. Florian.
So from my perspective, the config stuff doesn't really work for removal because it tends to get compiled out. And if it actually impacts user space interfaces, then people are on a world of hurt who run older distributions with newer kernels or have container images that other people run on newer kernels. So I'm not. We have been through this with the vsyscall interface on x86, and this turned out to be, and still turns out to be, really, really massive because of the old user space dependency on that interface.
So user space interfaces, I think, are a completely separate category from what I was thinking of. So for example, to give a dependency chain, we have drivers for ISA bus cards, like a SCSI card that is used in some old system. And we've frequently removed ISA device drivers saying these are for old systems. Obviously, nobody's using them, which may or may not be true. I'm actually not sure. But we do have systems that only have ISA slots, like some old 486 machines, or some Unix workstation from the 90s that had those slots. So if we have a way to decide at some point, all the machines that have ISA slots are now obsolete because we have checked with the people that were last running them, and they say they are not running them anymore, or there's few of them that we just tell them to go away, which probably won't happen. But that would be a case. We assume that nobody's using this, and there's no user interface. There's only a hardware interface between the kernel and some device. The user space should not be impacted by this. Does this make sense to you?
Yes, to some degree, but it for the syscontrol removal, for instance, I think a primary mover was that the StrongArm Netwinder platform, I think that was a theoretical user of that, but yeah, the X server would have used that for IOPL emulation or something like that, and we figured out that that was really necessary anymore, and that led to basically to a user space API change. And a lot of distributions already had compiled it out, so it made the decision easier. But yeah, I think there's still a point where certain applications bubble up to user space.
Mm-hmm. Yes.
And I'm slightly cautious about this story in that area because of the container impact.
Right. So anything with the user space interface is certainly a separate category from something like we know somebody's not using this machine, so we remove the machine support, and nobody else is impacted because it's only machine-specific code.
It may also be not is nobody using this machine, but nobody is running upstream kernels on these machines.
Right. That's
this kind of more precise definition.
Yes, exactly. That's what I had. The last user stopped upgrading kernels is my definition of there are no more users, because if they are running a 5.4 kernel on it and we remove it in 5.9, then that's fine, as long as they will never update their kernel, and we know that. And for a lot of cases, that's actually something we can know. For a lot of other cases, it's something nobody knows.
What about cases where the drivers, maybe they don't even work anymore, like they've just been quietly broken by accident, by churn? Have you seen much of that in the broader kernel?
That I think that always happens at some point. And it's usually a sign that the code has been obsolete for a long time, and then we just remove it. So it's not something we need to plan for, in the sense that we know there are still users and we expect them to stop using it X years in the future. Because at that point, when we notice that something has been broken for 3 years, and the last update from somebody using it was 5 years ago, and before that they updated it every year, at that point we can just remove it. That's the easy case, I think.
Well, if we're going to have a pause, I just wanted to say that your removal of the architectures was I think, motivating. I know we removed a lot of large drivers as well after that went through, because it kind of got the ball rolling that getting rid of obsolete stuff is like acceptable to the community.
Mm-hmm.
So thank you.
I will.
Hello. Yeah, I recently had the pleasure of having to hack on 32-bit Spark page tables, and I got no comments for the patches that I sent. Very little feedback, and it turns out that actually there were quite a few users of that code, but it was all the CI bots were using it to test the color. The code only exists to be tested in some sense. But ultimately the CI bots did run that code. They ran it with QEMU. They found bugs in my patches and managed to get them merged in a way that they worked. I'd be dubious or nervous about introducing config obsolete or something like that if it meant that the CI coverage no longer worked, or if it was more difficult to run under QEMU, or if the drivers bit rotted, for example. Because at least from my experience with the 32-bit Spark code was that the CI was invaluable for that.
Yeah, that makes sense. Spark 32 is an interesting case. I also, like a couple of people in the last 6 months, have found very serious bugs in Spark 32, like System 5 IPC not working at all. And it turns out that there has been a lot of testing on Spark 32 user space, but only on Spark 64 kernels. Like all the glibc testing that was done was on 64-bit kernels, which did not have those bugs. So I'm also fairly certain that there are very, very few users of Spark 32, and they're probably all using older kernels. Like there's the Leon CPU, and the people who work on that, they have a fairly old kernel that they publish for their users.
All right, this is Len. Can you hear me?
Can you speak up a little, or move up the volume a little?
Len, can you hear me?
I can hear you, but you're not loud enough.
All right, well, I'm as close as I can get.
Okay, that's good.
I wanted to build on what Jonathan was asking about feature removal and turn it around and say, what did we learn from the feature removal? It was invented with best intentions. What did we learn from that experience? And what are we going to repeat from that here?
Mm-hmm.
Right?
Yeah, I don't really have an answer for that. So when was that actually?
I don't know when that was, but I can tell you what my impression was. And my impression is whenever this kind of thing comes up, and that is that, if you'd sit down at the Linux kernel summit with Linus, he's basically a pragmatist, right? He'll say, you can't break an ABI unless nobody notices, right? Like, okay, well, that's an interesting rule, right? And so it's sort of like you can't remove something unless somebody notices, right? The fact that you put it in a file and then you said in 2 years I'm going to remove this, and then you remove it and then somebody's upset in 2 years, it doesn't really help that it was in a file, right?
Mm-hmm. Well, that's not, as I said, it's not the idea to plan when we will remove it. It's more like when I researched the 8 architectures, there's so much information that you try to gather to find out, is anybody using it? And if you have the information that, yes, there are users of this bit, I want to document that so the next person doesn't have to look for it.
I see. So basically, what you're trying to document is something that's not obsolete.
Yes. Well, it's for obsolete hardware, but where the code is not obsolete yet. Well, if we know that the code is obsolete, then we should just remove it. If we have proven that the last user has gone away years ago because the code is already broken.
That's the existence proof, right? And that's what we've used before, right? Alan Cox would say, oh, yeah, you have to update that. And if you can't test it, no problem. Because if nobody notices it's broken, you're done, right? And if nobody notices and it's been broken for a long time, then perhaps you can remove it because that's proof that nobody's used it. So it's sort of like you're adding poison, right?
Yep.
But it seems like a mechanism like that is actually quite pragmatic. I mean, it sounds sort of, childish, but it's actually quite pragmatic. It's a factual existence proof where documentation, who reads the documentation, who updates the I think the reasoning for getting rid of for other documentation was, oh yeah, it got updated, it got written, it never got updated, nobody read it, and nobody obeyed it. So what was the point of maintaining it, right? All very pragmatic. Mm-hmm. So I think here we probably also need something that's pragmatic and along those lines, you know what I mean? I don't think documentation is really gonna, it might be a great place to stash some notes, sure, you can always do that, but there actually has to be a mechanism, don't you think? For it to be successful, like 5 years from now to look back, there has to be a mechanism that's,
We have a bunch more people that want to say something, and we only have a few more minutes. So let's continue with Laurent.
Yeah, just a small comment. I think this mechanism could also be useful for a bit of a different purpose. I've seen numerous times when doing video photonics development and doing subsystem 1 refactoring that people were asking who has this piece of hardware, because I'm not sure that's my code is correct and I would like that to be tested. So if we had a way to streamline the process a little bit and help to find people who could test something, that could also be useful in some cases.
Okay, good. Yeah, James?
Well, what I was going to say is we have a form of lens existence proof in SCSI anyway. I mean, what we do is we just keep drivers around forever, as long as they cost us nothing to maintain. The problems come when we actually alter the kernel ABI, and then somebody has to sweep through all drivers and they start bitching about the obsolete ones. And then we start to discuss whether we should actually keep them around, update them, or just get rid of them. But the point is that it's a fatal, if we decide to get rid of them, it's fatal at that point, because then nobody can actually do anything to update them or anything. Resurrecting them from Git is a nice theory, but it never works once you've done this.
Mm-hmm. Yeah, so one more last thought from me. One thing I noticed in the past many times is that when a maintainer goes away, they really, they were the last people who knew that nobody was using it, and then they went away because they took a new job. But that means it's nobody's job anymore to remove it. And this would be something that we can help with. Okay, and my time is up, and let's continue with Guoren and the K-probes jump optimized op-probes for more architectures.
Okay, thank you, Anne. Okay, my voice is clear, Anne? Can you hear me?
Yes, very good.
Okay, thank you. Let's begin. Okay, my name is Guoren, and I'm from Alibaba T-Head. And today's my topic is about K-probe jump optimized for more arcs. Yeah.
You have the presentation, and you should have. Yeah. Okay.
Thank you. And a little bit of self-introduction. I focus on our product, our CPU products, and we have two ISAs. One is RISC-V 64, and one is SysGuide 32 bits. And more details you can visit our website. And I'm also the SysGuide subsystem maintainer. Yeah. And next. Okay, recent work I focus on the KPROB. Yeah, I have implemented the SysGuide, SysGuides, and include F-trees, KPROB, and a lot of related stuff. It's a little bit lonely job. And now I'm working with the RISC-V KPROB, and I have done the KPROB implementation, and the patch is under reviewing. And I also made some puzzles, so I bring them here, and looking for some helpful and advice. Yeah, and any advice are welcome. Next. And I have some, here is some of the statics in the current kernel tree, and you will see, currently optimized, KPROB jump optimized, just 3 ISAs support are implemented, PowerPC, and x86, yeah. And my goal is that, my work is that the RISC-V SysGuide support the features above this year, yeah. And why we need the optimized jump, KPROB optimized jump, because it will get better performance. Traditionally, the KPROB is put an e-break in the instruction flow, and you will get 2 exceptions. One is the KPROB breakpoint, and you will in this exceptions you need to you could call the pre-handler hooks and the post-handler hook. Sorry, and the second. And you also need to single step to replace the instructions. There are 2 ways, and one is single step, one is simulate directly. Single step will cause another exception trap, and the RISC-V don't have the single step exception. Most of us use the single step exception, but the RISC-V don't have that. But it's very easy to solve. Just to put a breakpoint behind the replace instruction, and it will cause another exception. That is the problem. You will see, okay, two exception is very expensive, and the normal KPROB and the normal KPROB is the very bad performance, and the boosted one. The boosted means the use the simulated way, and the simulated won't cause the exception. It just directly simulate the instruction by modifying the ptrex in the stack, and if we use the jump optimized KPROB jump optimized will bring our high performance. You will see, because there are no exceptions. Yeah, and I think the boosted one and the normal KPROB is the same, because half equals nothing. Yeah, some of them may be different, but I think so. Yeah. Okay, let's see here. How the KPROB jump optimization work, and he just replaced the e-break to the branch. Yeah, and that means first you need to set up a data buffer. The data buffer is one-on-one with your probe point, and this is just like a trampoline, and you just change the e-break to the branch, and when the instruction meet branch, it will jump to the data buffer, and it will emulate the exception behavior, save regs, and the callback, and restore the register, and directly execute the instruction, replace the instruction, maybe 2 or 3 instruction or more. Yeah, and then trampling back to the original execute pace. Yeah, that is how KPROB jump optimization work. Yeah, this is the background technology introduction. Now let's see how current architecture implement the optimized KPROB optimization. Yeah, and first one is x86, and for 86 and have very scalable instruction length, 1 byte or 5 bytes. Yeah, and he have a 5 bytes branch instruction with 2 gigabytes range to jump, and he also gathering the text and module together into the into the 2 gigabytes. So it's could cover text and module. All the replaced instruction must be relocatable because some instructions are PC relatives and they are executed in different program counter. So we cannot directly execute a PC relative instruction, and we need to prevent it. And x86 couldn't reuse the kprob single skipped. That means simulate ptreg, simulate replace instructions by modifying ptregs, because he maybe will replace 2, 3, 4, 5 instructions, not 1 instructions. Yeah, so many instructions. That's the 86 implementation. And second is ARM32. Yeah, ARM32 is much more better, and all instructions are 4 bytes aligned. That's a fixed instruction length, and that means that only 1 instruction was replaced, and you just deal with the 1 instruction is much more easy. And using the branch instructions, and he have the 24 bits range instructions. Yeah, and he also gathering his text and module together, and he occupies some range of the user space, module address space. So it's work okay, and some non-relocated instruction could be simulated because he only 1 instruction, so it could reuse the kprob single-step skipped simulation mechanism framework, and it's easy to do that. And I found some strange things is ARM64 didn't implement this feature. I don't know why, because they have gathering together, because they have gathering together, and seems all things is ready, but I don't know why he didn't implementation. Somebody has asked this. Somebody has asked this in the mailing list to the functionality. Yeah, BBC functionality, and it's really valuable to feature. Yeah, kprob optimization. Okay, let's see, the last one is PowerPC. Okay, let's see, the last one is PowerPC. First, the PowerPC, all instructions are 4 bytes aligned. The same with the ARM32, and using branch instructions with 32 megabytes range. Yeah, and it's also the same with the ARM32. But the strange is he has only 1 optimized instruction slot there, and that means that means that's only 1 optimized probe is there, and you will see the implementation is here. And he put the data buffer here, and if it's in use, then it will reject to optimize kprob point. So there's concurrently only one kprob point there, so it's not good implemented. Why? Because the COM instruction page allocation is from the module area. So and the module area is very, very far away from the text, so he put them together. Yeah, and I think the PowerPC maybe should re-implement it with us. Yeah, join us and improve it. Oh, please.
Yeah. Hi. Sorry to interrupt you. So just a small clarification there. We do have a single opt instruction slot, but the slot is actually a 64K page, And this is actually something that we include as part of kernel text. And we are actually able to optimize a lot more probes. As in the slot is a single one, but we break that up into multiple trampolines. And I think we can optimize around upwards of 100 up probes at a time.
Oh, okay.
It looks like it's a single one, but it's just a slot that's single, but we are able to optimize more. And what you pointed out about the module text is correct. Right now we are not supporting that, but we plan to do that. The idea is to just allocate a few module relocation stubs that we'll be able to reuse to jump into the trampolines.
Yeah. Thanks point out my mistake. Yeah, and
No worries. Yeah.
that you just the one page in use. You just the one page and not one slot and maybe several slots. Yeah. Thank you. Thanks for pointing me out. But I think you can come with me and we met the same a lot of stuffs and okay. Now let's continue. And what's the matter? How to and I don't know how to next stage.
Let me try.
Help me. I want to next page, but it's currently.
Is it the page you wanted? Go.
No, I have several pages behind. Let me see. Okay.
x86 ARM Powerpc. Do you see the slide?
No. Okay. I couldn't see the slide. Can you hear me? Somebody could hear me?
Yeah, I hear you, but somehow I don't see you in the list of the users.
Okay.
So I can move slides for you if you'd like to.
Yeah, you can see the next slide.
We see the slide awards x86 silver, ARM32 gold, Powerpc bronze.
Oh, okay. I think my. Okay. Wait a moment.
Should I move to the next one?
Yeah.
Puzzles of RISC-V and C-Sky.
Oh, sorry. I have. Okay. My slide is frozen. I couldn't see next slide. I will.
Wait, I think Go just disconnected. Go, do you hear us?
Microphone symbol seems white, which I think means that his audio is disconnected. I'm not sure.
I think he's reconnecting, and let me try to make him a presenter again.
Yeah, we'll be going through the echo test, I'm afraid. That can take up to 30 seconds.
Because he disappeared from the users list for a while, and now he's back, so maybe we can continue from here.
Maybe somebody else has something to say about this slide. Any comments?
Maybe Masami.
Can you hear me?
Yes.
Oh, sorry. I'm back.
Okay, we have two of you. Let me see if this. Okay, can you move the slides?
Okay, I can move slides. Thank you. Okay.
Great.
Okay, sorry. Oh, no.
Things happen.
Okay. And okay, I have introduced 3 architecture implementation, and since I have, yeah, and ARM32 is the best one because he has the most opportunities to optimize the kprobe, and the 86 is next one because he didn't implementation the single step skip, and that means some PC relative the instructions couldn't be optimized, and I 5. Hello, Masami.
Hello. I have a comment because the x86 also were implemented that the single step skipped. All the optimization is implemented started on the x86.
I mean, in the optimized callback, he didn't call the single step mechanism in current kernel tree, and the 86 will occupy more instructions that will decrease the opportunities to optimize the kprobe. So
yes,
I put second to ARM32. But this award just for the kprobe optimization, because ARM32 implementation didn't cover the standard tool. You mean that's a limitation for his architecture, and the fixed instruction set is bad for the code size. Sometimes I think, so it's just for the kprobe optimize, and I hope the PowerPC obviously is not very good, but I think maybe we can together to improve, really implement it, and together, But he is better than other architectures because these 3 architectures implementation that. Okay. Let's see what puzzles I have met in the RISC-V and RISC-V. First, we don't have the pop jump instructions, and the jump instruction only have RISC-V only have 20 bits. That means only small range, and RISC-V only have 16 bits range. So we don't have the pop jump instruction. Second, all of us is the 2 type of the opcode length. We are half word and 1 word opcode length. So it's a little bit not simplest as the like, and our text are not optimized for this. They are all far from for the modules. And maybe we could. It's easy to tuning that to port in software, I think. So so one solution is solution 1 is I mentioned is we don't have the proper branch instructions, so we need 2 instructions gathering together. And first, maybe we should reserve some clubber registers, such as the same like similar to the ARM64, and with 2 instructions, prepare 20 bits and 12 bits, and then we got 2 gigabytes range, and total cost is 8 bytes a line, 8 bytes length, and we also redesigned the module's memory layout close to the 2 gigabytes range, similar to the x86. This is the solution, one solution, and I think maybe it's helpful for the PowerPC use the same way, or is some bad effect? Any question here? Feedback here? Solution 2 is we use pseudo instructions, and it will get a very large range of the value, and then we can directly jump there without changing the memory layout. Obviously, solution 1 is more suitable, but we need to ask the RISC-V ABI specification, because ABI specification have defined all the registers. Yeah, and but I think for the compiler, maybe compiler couldn't utilize all registers. Just reserve some registers is okay. The same, just like what 64 have done. Okay, and next.
Hello, Go.
Yeah.
Hi, Go. Did you check that there are some papers from the Paradigm project?
Paradigm, yeah.
Yeah, I wrote that the web page on the chat. Actually, most of the ideas about the jump optimization method itself is for RISC processors written in these Paradigm papers. Maybe you can find that. Yeah. For example, making trampoline buffers near the text, and jump into the trampoline buffer and change the save the registers and make a long jump from the trampoline buffer to the final position.
But that's a little bit complex. I mean, we are trampoline to the destination, but okay. Maybe we could talk about this in the mailing list. That's because we should find a way to implement that, or we will. I couldn't finish the work yet. Yeah. I need a solution. Yeah. Thank you. Okay. Okay. And the solution. Okay. This guy is similar, but okay. Maybe time is nearly up. And here is the nice idea of the optimization to the K-prob. And I call it shadow program counter. Yeah, shadow program counter. That means you put the instruction before you replace the instructions. That will change. That will set your SPC. SPC will let you replace instruction execution when the PC counter value is from SPC, not program counter. Yeah, and I will where the value is from the constant value. Literal pool. It's a literal pool style instructions. Yeah. Why I need this instruction? I will mention later. Okay. I almost finished, and easy for hardware implementation. I think here is the picture I searched from the Google, and this picture is very the simplest picture of the pipeline MIPS, and what we do is put some. Look here. Can you see? Yeah. Okay. You can see I just put SPC near the PC. Yeah, and the shadow PC, that means hijack the value, the result of the execution pace, but the original instructions are all still from the original PC count, and fetch the instruction from here is the same. But when the calculation is from SPC, and the calculation. So the execution, the replace the instructions could be executed correctly in this way. And why I use and set the SPC is the long pace. Set the SPC is long pace. So we could use some predictor mechanism to improve this mechanism, hardware mechanism. And that's that. And I think it's a lot of details of hardware, but it could implementation. And this mechanism won't affect the pipeline stage, and won't stall the pipeline, and it could let the process speculative execution fast, and no effect of performance. Yeah. And second, and the benefit is we could prevent amount of the modifying in PTRIG simulation code in such as in ARM. I think that that's really a boring code, and we will prevent that. And you know, RISC-V have a lot of customer instructions there, I think, because a lot of our customers want to invent a lot of instructions, so we really don't want to care about this. We hope the our operating system could handle all of this. Yeah, and so I don't think simulation code is proper to in our architecture directory, and it could bring us a better performance than simulation than single step. It's with better performance, and it will increase the opportunities to optimize the K-prob. So here is the okay. Thank you, and I want to can I have a vote here to
just last word, and then we can postpone it till the end. We have some spare time in the end, so we can restart the session of K-probs if you would like to.
Yeah. Can you have a vote here to see to get? I want to get some feedback from audience about this proposal. Yeah, and you just yes or no. Yeah.
Here I see Masami proposes to go to a hack room and continue the discussion. We have a spare time later. Probably it's too late for your time zone. I don't know. Or you can choose any of hack room and stay there with Masami.
Okay.
Thank you. Thank you, Go.
Thank you. Yeah.
We now have a 10 minutes break, almost 10 minutes break, till 3 p.m. GMT. So see you back in 6 minutes.
Okay, cool. Cool. Yeah. Oh, sorry.
Let's wait a bit more for.
Are you starting the next? Are you picking the presentation?
Yes, I'm picking. It's not really presentation.
It's yours anyway.
Okay. Right. So I looked for a volunteer to do moderation of this session. I couldn't find anybody, so I'll do it myself. Anyway, I think as most people are ready, at least more or less half of them. There is a lot of code duplication, copy-paste in the Arch code. If you look at several architectures at the same time, more or less, you see who copied from who and how it all evolved. And it would be really great if we can improve what is going on there and factor out common pieces, use generic code whenever possible, and even if some functionality is relevant only for 2 architectures, it's still worth making it, moving it somewhere to kernel proper, like lib or whatever it belongs, and using it from there. So the only slide I have here is what can we do about how can we raise people awareness, how can we improve the process, and I really would like people to speak up, because to be honest, I can't say I have much ideas how to do this, except that people should be willing to do this, and well, and
yeah. So the process that we used to have in place was that every time a new architecture was merged, when I reviewed the architecture code, I would ask the people to generalize more of the code that they just copied from the previous person. But I don't think that's going to work in the future, because there's not a lot of new architectures coming up these days.
Probably no. And there's still a lot of copied code everywhere, and there are still new code that gets to a particular architecture, but probably it could be generic, and it could be used by more than one of them. I won't pick names, but some architectures are more greedy than others.
Yes, you all know who you are.
Yeah, I think you need to get some of the maintainers buy-in here, and the current Arch maintainers. And one example was VDSO. We pushed back on getting more code in there. We asked for it to be made generic, and well, luckily we had to an engineer to work on that. But that's make sure we get the maintainers buy-in, and then as you go, start improving something.
Okay, you'll be first.
I don't think I am the first, no. There are, lots of things like the MMU gather stuff, that's a lot of the TLB stuff that was generalized by the MM people. And I think
actually it was Peter, I think, mostly.
Sorry, please go.
I think TLB Gather was mostly x86 people, actually. It was Peter's project, I think. But, yeah. So, I don't know. I wouldn't say that proposing documentation would really help. It's not that we're going to follow it anyway. I don't know. I know KVM folks have been discussing it for a while, but I can't say I really followed their discussion. I know that they were trying to move pieces as much as possible to generic KVM out of the architecture implementations. I think this applies to other pieces as well.
One area that I still have on my plate and have had for a year now is the system call tables, which are now in a mostly generic format to make it so that you only have to change one file for adding a new syscall, which has the advantage that it's really easy to add a new syscall and has the big disadvantage that it's also really easy to add a new syscall. But I think we should still do it.
I think it's more than one file, but still.
Well, right now you have to change something like 15 files, and I would like to have it be only one file.
15 files. I just did it. So yes, one place. Absolutely. Please do it now.
Okay.
There is a from a history perspective.
Mark?
Only way
no, let Thomas go first.
Sorry.
Thomas?
Yeah.
Thomas, you're way low in volume. You need to turn up your pulse audio or get closer to the mic.
Better now?
Yes, a bit.
Let me move that up. Before people complained my mic was too loud.
Well, look at it this way. We're always going to complain. We just like to hear you. So we're complaining legitimately.
Oh.
So, better?
Yeah.
I can do more.
No, a little less.
Yeah, okay.
Why didn't you push the boat out and try video?
Okay, so from my experience, and I have done a lot of this generalization stuff, it always takes someone who actually starts the work, at least provides generic infrastructure. It's not necessarily required that the same person converts all the architectures over, but you have to make an incentive to convert it over. Like we said, okay, we're going not to go to support VDSO time namespaces outside of the generic VDSO, or we are not going to support X outside of some generic implementation. That worked pretty well with a lot of things.
I think you're right, but there's still, what I see that people that work on a certain architecture, they implement some feature and they implement it for that architecture only, and they do not think of probably making it generic or creating a generic framework that is only applicable for one architecture at the beginning and then can be applied to others.
So what I was going to say earlier is that for a lot of features when they get added, and I think actually time namespaces is a good one as an example, system barrier is another one. While it's a generic piece of functionality and we can plumb in a generic syscall, there's actually implicit requirements on each architecture where the best placed people to actually implement those implicit requirements are the architecture maintainers or people close to the architecture rather than people close to the generic bit of syscall code. And due to that, I think that saying you have to enable it generically all at once isn't really viable, because people will not be able to do everything, will not be able to do all the necessary bits for all architectures at once. We're still going to have to opt in per architecture as you implement all the necessary bits and pieces.
Thomas?
No, well, didn't want to say anything.
I think it's a different. There are two sets of problems. There's the one where we want to get a feature enabled on all the architectures, but then we need some work to be done from architecture maintainers, or the feature won't be available. And the other problem is every architecture maintainer copying the implementation. And I think the second one, which is the one that Mike was actually
this is more severe, yeah.
Yes.
Sure, I agree
But
with that. I just meant fiscal table example. I think that it doesn't really solve that problem. That solves the other problem.
Yeah.
I mean, the copy and paste problem exists forever, and so I mean, some stuff starts out as the community looks at it like, oh, this is very, very architecture specific, and a couple of years later you realize it's completely bullshit and it's just generic code. So, but then you already have 25 different versions of the same thing and 25 differently buggy versions of the same thing.
I think that's the thing with
So I
a lot
agree
of
with
coders.
that, but I think if you're lazy enough, people can actually not copy and paste. I know when I was doing stuff to PA RISC, I tried to see if there was a generic implementation. Part of the problem is people make generic implementations really hard. To get something generic, you usually have to split it up into your architecture-specific piece and your fully generic piece, and get upstream to take the fully generic piece. And that's usually a multi-release process as opposed to cutting and pasting it and putting it into your own architecture, which you control. So we are, in a sense, blaming people for refusing to take on this pain, a pain we create. I hear rustling of papers, Thomas, but no comeback.
Did I miss a question?
No, I was just saying.
It was a command that James expected you to respond.
It was a comment that I agree totally with what you say, but we make it hard. We make it too hard for people to do, and it's much easier for architecture maintainers to do the cut and paste. Just take everything into their architecture and maintain it, rather than try to split it out nicely into a generic plus an architecture-specific piece.
I don't think we make it hard. It's just a lot of more work than doing it right away in the architecture. People are happy if somebody does the heavy lifting of creating that generic piece of code, then people are happy to convert their architectures over. But the other way around, coming up with the generic infrastructure first, it's, you know, the time to market thing.
I don't disagree, but I think we do need to try and make it easier for people. I mean, people will do generic stuff. They'll do the right thing if we make it easy for them to do it. You just make it too hard. And while you said it's not too hard, you said it's a lot of extra work. So to most people, those are equivalent, right? So just because we make it a lot of extra work, people don't do it.
And again, time to market.
But again, it's extra work. I mean, you have to think way harder about the generic infrastructure than about the cobbled together thing, which makes it kind of work in your architecture specific thingy.
So are you offering words of encouragement or discouragement to people who want to do this? Because I hear discouragement.
I guess the question to ask here is, are we actually solving anything by arguing about where the problem originates from, rather than saying, what do we need to do going forwards? Because I think for a lot of these things, the major problem is that there's a lot of legacy per architecture. For example, all the syscall restarting bits happen to be architecture specific, and the event return to user space stuff, which Thomas has implemented a generic version app and core code in the last merge window, but it's obviously going to require a lot of work to massage existing architectures to move them over to that, and to fix that core code to do all the things that all the architecture needs to do. After that's done, what sorts of things are people copying and pasting that we can know, that we can predict and avoid, or is it something we just have to live with and deal with?
Well, right at the moment, we have to live with it because it's the system we've created. If it's too difficult for somebody to do it up front, and we're not even sure they'll do it right, which means we're discouraging to them, we have to see how the interface works out and then fix it afterwards, which is basically what we've been doing for the last 20 years.
So do we need to change that approach at all then, if it seems to be working? And we just need to pay attention to it and fix it up as and when?
That was part of my question. I mean, this thing started with the hope that we could get architecture maintainers to do the right thing. And then we started saying things like, oh, but they don't really understand how to do it generically and it's a lot more work for them and they wouldn't do it anyway. So we come back to the conclusion that there's no way we could get them to do the right thing, even if we could tell them what it was.
I mean, you can get them to do the right thing by just telling them that yet another copy of the same thing is not accepted, period.
It's their architecture.
If you put a stepping stone into somewhere which prevents them from getting their feature upstream, they will go a great length to actually do it. But most of the time, nobody puts a foot down.
Right, but just saying no is not a good enough encouragement. It's already difficult enough being an architecture maintainer. Now we're just going to beat them over the head. You know, the rolled up newspaper trick. Every time we do something we don't like, they're really not going to like that. It's like training a dog. It works much better if you use rewards than punishment.
Yeah, but you'd still have to tell the dog no. And if he obeys, then he gets a reward.
Right, so what's the reward? Well, you've told us what the stick is, which is saying no, which is a pretty big one in Linux, because it basically means sort of releases and releases of wrangling over a feature, which everybody gets to hate in the end. What's the reward? How do we encourage better behavior?
For me as maintainer, the reward is less code for me on the ArchChamp 64. Just try to push it out, give it to Thomas.
Yeah, that's the same for me when I was doing RISC. When we had some memory management issues way back in 2005 that I tried to make generic in the kernel. And I spent years of pain doing it. But when I look back, it would have been so much easier for me just to cut and paste everything into PRS as everybody else did, than try and do it generically. And it just happens that 15 years ago, I was sort of blue-eyed and innocent and thought, oh, I should do the right thing.
I think there's maybe a bit of a chicken and egg problem here, which is that it's not, I mean, it's obviously not possible to design a generic interface until you've got enough diverse users or implementations that you can see what the common behavior needs to be. But then by the time you've got that, you've probably got, I don't know, 2 or 3 architectures that have got their own maybe copy-pasted implementations, but probably slightly tweaked, which work reasonably well, and they might even have user ABI. So then convincing them to switch back to this generic implementation, which has got very little testing, I suspect, at that point. It's not always an obvious choice. You're kind of asking the architecture maintainers to take on this burden of switching to yet another implementation, which they're probably not being paid to do, yet they will have to deal with all the regressions. So it's swings and roundabouts there. It's hard to know how to break the loop.
But those should be shared regressions, right? They should be shared among all architectures, at least the ones that use it. But I believe I also heard you give a vote for the status quo buried in that.
Yeah, I don't know. Like the entry rework's a good example from Thomas. I know that's just gone in this merge window, and you know, quickly some regressions have been reported. So at least from my point of view, I'm not hugely keen to jump on that. But maybe once it's settled down, then certainly.
So just to be clear, for the ARM64 stuff, I've been slowly reworking our entry assembly into C for a number of years now. And I can tell you that the generic stuff that Thomas has got is not quite right for some of our needs and will need to be reworked. In addition to any x86 specific regressions, there would be regressions if we were to immediately move over to it, unless we massage it to support a more generic interface than it currently has. So there's 2 sorts of regressions that are possible there, James.
I mean, you always have to start at some point, and I try to take other architectures into account with some of the callbacks, which are optional. It's probably not perfect.
Sure. Okay. I didn't mean that as a criticism at all.
No. I didn't take it that way. No, I just wanted to say you have to start somewhere.
Yeah, you have to start somewhere. You have to slowly iterate on things to make them more generic. I think that's the way that we've worked for the last couple of decades. I don't see that we can make a significant change to working practices without putting a giant blob of work up front that no one will have the knowledge to do.
No, I'm not asking for that. So I mean, the main reason why I was moving that into generic code is because we spent an awful lot of time getting all the ordering constraints and all that crap correct, and letting everybody else do the same thing instead of building upon what we already have is stupid.
Yeah, completely agreed. Sorry, have I got slightly louder now?
Not as loud as Thomas.
I think my computer's decided to use the microphone.
It's better. It's better. Yeah.
Headset, so I'm just having to lean forwards.
Yeah. One of the things that Zoom does that this platform doesn't is it does a good job of level setting everybody.
James, it's off topic.
I thought we only had 5 minutes left.
We have 3 minutes left now.
Okay, what's the next topic? As in the next topic within this topic.
Arndt has something to say.
Yeah, one more observation is that we seem to be increasingly focused on a smaller set of architectures, where it used to be x86 and then nothing, and then like 10 architectures that were fairly active. Now it's more like we have x86 and then ARM64 and then a couple of others, and the rest doesn't matter.
We have like 5 active architectures. Then
yes, depending on how you count, something
3 lively architectures and the rest, I think.
Yep.
If you look by amount of interaction on mailing list commits and everything, it's below 10 for sure. The architectures that get some traffic and get some patches from people that do work on that architectures, and not from people like me or Christian or you, for that matter.
So one interesting thing we've never done is to have like a primary and secondary architecture as a concept. So if we were to define what are the primary architectures at the current time in Linux, we could mandate something like a new feature that is cross-architecture should work on all the primary ones, which could be something from 2 to 5 of them. And that would make it more likely that it's generic enough that it will also work on all the others.
I suspect M68K people won't agree with you.
Well, there won't necessarily be anything wrong with implementing the same thing on some of the other architectures. But if we like saying that a new major feature, you can't just implement it on your one architecture. You'd have to do it on all the primary ones, and then possibly on the ones that care.
This may be something we can ask people doing, but I also can't see how we can make it a hard requirement.
Yes, also agreeing on which ones are the primary ones is going to be hard.
Just having a mandate to implement a feature on more than one architecture might be sufficient as a starting point. Doesn't matter which 2 they choose.
Well, if it's 2, it's clearly x86 and ARM64. I don't think there's a lot of disagreement about that. But then what the third one is and that may depend on the feature.
Okay, and this time is up. This slot is going to end, and I'm transferring the control to Vincenzo. Vincenzo, can you click? Please check that it works for you.
I am trying. Just a second. Yeah, it seems working.
Great.
Thank you.
So it's all yours.
Thank you. So good afternoon. this has been an interesting year for the VDSOs. And I'm here today to present you some of the terms of this unexpected journey. It all started with an investigation on how to implement the compact VDSO layer in ARM64. And then going forward, due to pushback of the maintainers, we ended up having a fully featured generic VDSO library that has even its own headers. But let's begin. So today we will go through a brief introduction on what are VDSOs and why they exist. Then we will have a look on what it has been done till now. And then I would like to present some ideas on what I am currently exploring in order to get some feedbacks and maybe go back home with new ideas to explore. In the end, microconferences are for this. So let's begin with a brief introduction. We all know what are VDSOs. So they are a virtual dynamic shared object. And they are a shared object that are mainly intended to provide virtual syscalls in user space. They are around since 2005 in the kernel, and they are linked during the compilation of the kernel, and they are mapped by the kernel in every user space process. But let's see how this works. So all is initiated by user space with an exec-VE. Once the exec-VE recognizes that we are dealing with an ELF, passes the control to invokes the ELF loader, which for the case of VDSOs basically maps the code and data page and sets the sysinfo header in the auxiliary vector. At the end of the execution, basically what it does is passes the control to the dynamic linker that for what concerns the VDSOs again checks that the sysinfo header is set. And if it is set, it links the VDSO shared object. And then when the control is passed to libc init, it checks if the symbols are available. And if the symbols are available, it sets the function pointers. Otherwise, it has a mechanism to fall back into system call. But let's see what does this look like. So basically, what happens is that we have two pages currently. One page for the data that is read-only mapped and one page for the code. And when the kernel executes timekeeping update or set time of day, basically updates the data into the VDSO page. And when a call to the VDSO code happens from the user space, what the VDSO library does is check the information that it needs into the VDSO data and returns the information to the caller. So yes, this is all fine, but how did we get to having unified VDSOs? So basically, the idea is more or less what we were discussing previously in Mike's talk. And we could divide these into three main points in time. The first one is certainly the unified VDSO. Then the second is what it happened with unified headers. And the third one is the recent activities that are going on into the VDSO space. So mainly for the unified VDSO, the main reason was that prior to the introduction of the VDSO library, every architecture had its own code implemented in its own VDSO library implemented into architectural code. So this clearly meant that we had a lot of duplication around the kernel. So the main purpose was to investigate and find the commonalities and try to find a common path to define a common VDSO library. This has been done through basically generalizing a lot of the VDSO code that is now used to generate the VDSO library. So at this point, basically, what we noticed immediately is that there was a long dormant problem in the kernel due to the fact that the VDSO libraries implemented in architectural code were relying on the Linux headers. But being the VDSO library, user space library mainly, being a completely user space library. So what it needs to do, it needs to basically rely on a subset of the Linux kernel headers that we extracted from the headers, and we put into a new namespace that we called VDSOs. In this way, basically, we solved some compilation errors around the kernel or some other fancy stuff that happened around. Was there someone that was trying to say something? James, I saw you.
No, sorry, I'm typing another email. I must have forgotten to mute. Sorry.
Oh, that's all right. Yeah. So basically, once the problems of the headers was sorted, we saw a lot of recent activities that leveraged this VDSO work. RISC-V introduced the VDSO support based on the unified VDSOs. Powerpc porting and the S390 are on the way, are currently discussed on the list. As Thomas was mentioning in the previous talk, the time namespace leveraged the unified VDSO work. Basically, both the x86-64 and ARM64 portings of time namespace have been currently merged as of 5.9 RC1. Now, so this is the current status, but what's next? I tried to ask this question to myself, and basically I tried to explore some ideas that I would like to present to you today to get some inputs and to see if the direction is right. And yeah, to more generically have a discussion. So first of all, I think that let's agree on a VDSO principle. And the VDSO principle that I would like to agree on is that we do not have to enter the kernel. We don't want to enter the kernel if we don't have to, because it's costly. If we try to explore normal Linux distribution and see how this principle is handled today, something that is clearly evident is that libc tries to help with this approach because it does not do system calls if it can avoid them. And in doing so, it takes advantage either of the VDSO library or tries to cache information. For example, get PID after the first call is cached. But in doing so, the libc adds complexity because, for example, to cache correctly get PID, it needs to understand concepts like fork or clone and so on. The question that I asked to myself is that since we have the VDSO library already in place and the model is already there, should we try to simplify this caching mechanism and then maybe provide this information via the VDSO library in an efficient way? So obviously, this would give us, sure, go ahead, sorry.
We actually removed the PID cache from glibc because it was too broken with people directly calling clone. So it would be really nice if we got that into VDSO. We still have a TID cache for the recursive mutex implementation.
Let's say that I noticed it, and this is the generic approach that was there in the libc, and I have a slide afterwards in which I treat deeply what I tried to do. Anyway, I have few system calls that I tried to play with, and I would like to present here, but let's not go too fast. So in the coming slides, I'll provide some details on this. So this approach obviously
go faster if you want to get to the slides in the last session.
It's fine, Catherine. I have the time. Don't worry. So basically, this would give a simplified implementation and would obviously improve the memory utilization. No caching needed for anything, but obviously raises some questions. And these questions mainly are, which information do we want to make accessible via the VDSOs? Are those private to a process? Is there a risk if another process tries to access them? And if we keep this information in the global data page, shall we use an approach that is per thread or per CPU? And last but not least is, shall we make the VDSO page writable to have more syscalls that we could implement like that? Obviously, the last question poses a security threat, so I would like to leave it out for now and maybe have a wider discussion on this topic. But I tried to put myself in a real case scenario, and I took a Linux distribution. I tried to explore only the getters of the defined zero class of syscalls. I put in place my very powerful tracer. You can see the implementation here. I instrumented the kernel, and these are the results. So to arrive to the desktop of a normal image that you download from the network, basically we have probably more than 1,000 system calls that we could avoid. But how do we do that? So I tried to explore a couple of scenarios, to be more precise, in order to do that. But obviously, I am aware that these are not the only possible scenarios. The only thing that made me go for this exploration is that they seem fitting better the problem that I'm trying to solve. So the first one is utilizing the global data page and extending it with per CPU data. So how do we do that? First of all, we need an extension of the global data page. Obviously, if we add per CPU data, a page is not enough anymore, so we need to calculate a new size in terms of pages that we need to allocate, and this is, for obvious reasons, directly proportional to the number of CPUs. And then we need a mechanism that is architecture-specific, on which we provide to the user space the information on the offset of this set of pages in which the data structure for a given CPU is present. But obviously, this would be then read by the user space and extract the information from the data structure at that offset and return to the user the requested information. Yeah, the first I implemented this getPID because basically it was the simplest one to do. So the second approach is similar to the first one, but is per thread, and it uses a VDSO page that is private to the process. And it depends in the calculation of the page size on the number of threads. In this case, I've been a bit discouraged because as of Linux 4.1, I managed to find that there is a system-wide number of threads that we can set, but there is not a per process one. And this could have a huge memory impact if I would go on this way. But since I wanted to keep things simple, I tried to analyze the pros and cons of each one of the possible approaches. So obviously the per thread one offers a more flexible way of implementing system calls. Probably it allows to implement more. And if we can expose, and we can expose certainly process private data compared to the per CPU one. But the per CPU one reuses the global VDSO page, and so it is certainly a simpler implementation and is less invasive. And overall, it has a better memory impact for what I was mentioning about the number of threads. So since I wanted to put myself in the simplest case possible and try to experiment with a solution that I could implement in a short time and see how far I could bring the game, I decided to go for the per CPU one to begin with. So what does it look like, the implementation? So I extended, as I mentioned, the VDSO per CPU data. And now the offset depends on the SMP processor ID. The pages are allocated depending on the number of CPUs. And the way in which the offset is passed to the user space, as I was mentioning, is architecture specific. Let's see now how this is updated. So I implemented a new generic kernel VDSO-C relying on the generic VDSO library. I tried to use a logic that is similar in behavior to the update VSys call, but is updated during threads, start and switch. It currently uses only generic functions, so basically this makes the portability across architectures a bit easier, because the only thing that the architecture needs to provide based on my current set of syscalls that I implemented is a way to notify the offset to the user space and the fallbacks for the system calls. So as I was mentioning, this is what it looks like, the update code, and it is updated when a thread starts. It is updated again when there is a switch to the next thread, and then it is flushed and when we arrive at the end of when basically we flush out the thread. So now this is the implementation of the generic library VDSO for what concerns get PID. As it can be seen, the code is pretty simple. It gets the offset information through the arc get VDSO per CPU data, and then it extracts the PID and returns it to the user space. Based on this logic, I currently implemented mostly of the define zero class of getters. And I implemented even get CPU because I wanted to make sure that this is not something that is restricted solely to that class of syscalls. Obviously, I don't have an answer for how many syscalls we can extend this schema to. The implementation that I currently have has been tested on ARM64. But as usual in our world, when we end up defining an experiment, we definitely finish the experiment and have more questions than when we began. Hence, I'm glad to be here today, so you can help me answer to some of those. So if someone is interested to see what the code looks like, he can find it in my personal repositories. But now let's go to the questions. So I hope I explained correctly what the offset mechanism looks like. And I would like to ask to the other architecture maintainers, how would they implement this offset mechanism in their own architecture? So the thing that I did on ARM64 is to use a register that is read only for the user, and through which I pass the offset to the user space. So anyone wants to comment on this?
So I'm not completely convinced about like how much you can actually gain, even in the best case. Like you said something like 1,000 system calls for
yes.
getPID and a couple of others. Have you checked how many other syscalls are being called in the same time?
That's what I said in the previous slide, that currently I don't have an answer. I'm planning to do it. So the benefit in this approach is not only so it's even performances, but it's not only that. It's the fact that basically libc or whoever implements the user space can completely remove caching, doesn't need to understand kernel concepts anymore because it can rely on the VDSO to provide the information. When I was trying to figure out this approach, I tried to think to something that is completely unrelated to the kernel. To me, this looks like a lot as a push notification of the kernel, like the one that arrives to your mobile phone because it's the kernel that advertises all the informations in which the kernel doesn't need to be involved to upgrade. And this is the model to which, we could probably move on if I'm not saying that this is completely the correct approach, okay? It's something I'm exploring currently. Might be the next year I come with a completely different one, because maybe I hit a rock bottom pretty early and I can't implement many system calls with this one, as you're saying. But the answer now is that I don't know. So it's something that I'm going to find out.
One thing that's sort of bugging us on the glibc side is that the VDSO calling convention isn't the same as the user space calling convention. We still have to translate error codes to the TLS error value. And this means with a per process approach, that is not going to go away, because you don't have per thread data. And we already have one established case where user space donates a little bit of TLS space to the kernel. That's the robust mutex list. And with RSEC, we try to do something more elaborate, and there's also a TIT flag in there. So there's some overlap with what you were doing with your experiment. My question is whether there's a third option, not just the per thread pages and the per process or per CPU pages, but basically have a mechanism that user space donates a little bit of space to the kernel that's located relative to the thread pointer. And the VDSO knows about this donation and can then use this space for whatever it needs. And I would do away with the large per page allocation requirement.
Yeah, that sounds like an interesting approach. It's memory allocated by the user and provided through the TLS to the kernel. Yeah, it's something that could be explored as well. As I said, I am in exploration phase. I just need to see what is the right direction to do this. So the thing that I need to scope is what is the cost benefit of doing such a thing in terms of complexity and how invasive it is and so on. The approach that I was presenting is really small and it's not invasive at all.
Understood. But if we are doing this thing or we try to do this for RSEC, but we hit the ABI issues and the kernel user space integration problems. And if we have that complexity anyway for RSEC, maybe we can add a little bit more complexity and then use it for the VDSO mechanism as well. And I mean, it would be great if you just could use a new system call without a wrapper and glibc, just by starting using the symbol, and Ergo and everything will work magically.
I mean, so the idea is that to make this faster, we should really involve the kernel if we need to ask to the kernel to do some work. But if the kernel needs to advertise some information to us, like is get PID, for example, just something that the kernel sets and the user gets to know it because it requests it via system call. In that way, the user space can read it in another way. But yeah, I would like to work with you a bit more, even offline, if you are interested to Florian, so we can design something together and definitely try to see how far we can get with that. If this for you is fine.
Definitely, and we should also involve Mathieu for the RSEC aspect.
That's good. Yes, why not? Thanks.
Okay, thanks Vincenzo, thanks everybody who participated. We are now taking another 10 minutes break. Please be back in 10 minutes. It will be, let me see. It should be 4 p.m. GMT.
Okay, thanks.
Mark, do you hear me?
Yes.
So it's time for our next session on the generic syscall trap. And I think this is Thomas.
Thomas?
Mike, whenever you're ready, take him.
Oh, yeah.
Yeah. So I'll change the presentation entry LPC. It's a lot of slides here.
Yeah, exactly one.
Okay, and I'll mute myself for now.
Okay, so what we have now in the cool code is a generic functionality for system calls and traps or exceptions or whatever you want to name them. So a lot of the things we had in low-level assembly, like calls into context tracking, locked app tracing, and things like that, turned out to be outright dangerous. One of the really interesting problem cases was you had a breakpoint exception, and then you called into the tracer, which had a breakpoint set for code patching. So you ended up in a infinite loop of breakpoints. Great. Things like that. Then looking at all the architectures, all the same that the work is done on syscall entry, ptrace seccomp audit. And on exit, the same thing. You have the TIFF work loop before you return. You have final return work where you have to adjust things. And then finally tracing, locked up, and context tracking to get the state straight when you go back to user space. So if you look at all the architectures, it's either incomplete or it's totally differently ordered, and probably none of them is really correct. Similar things you have for exception entry or trap entry, interrupt entry. Same thing, you don't want to have anything else than establishing stack frames and really architecture-dependent low-level work in the assembly code, and then you want to call out into C and hopefully into common C code in order to get the same things which you need in syscalls. That means context tracking, locked up tracing. On return to user space, you have a similar functionality. Most of it is shared with the syscalls. And on return to kernel, you want to take care of potential preemption and then the state establishment again. One of the things we figured out very fast when working on it was that making sure that none of this code can be, or none of the code which is really interesting to protect against instrumentation, that you can't follow all the things which happen there. So you really have to have a tool, and Peter Silstra extended object tool to validate against instrumentation of truly non-instrumentable code. We have the tracers, we have K-probes, and all the other things which might want to inspect everything in the world, excluded from that, and that's really helpful. So I think most, or at least every architecture which is still maintained, should move over to that. I'm pretty sure that we have to make adjustments to that, but we have the same thing with VDSO. We started off with x86 and ARM64. Then Powerpc tried to use it and found some shortcomings. We've provided the fixes or the changes so to accommodate with PowerPC. Now, S390 had another request, which was already provided as an infrastructure in upstream, so S390 can go and move over without having any architecture-specific hacks anymore. So that's pretty much what I think should happen with the generic entry code as well. There's a few things why I think it's really important. One, things like NOHAT's full locked-up tracing and all these kind of things really need to have the right ordering, and we want to control them in one place and not in 5 gazillion places all over the architecture tree. The other thing is for people who add features into the TIFF work loop on return to user space, both from syscall and exceptions. Right now, if you want to do that, you have again go through 25 architectures and miss out half of them. So that's also easier for things to change, for things to update and add new things into syscall and trap entry exit over time. So that's pretty much what it is, and my question is what are the opinions of architecture maintainers, and what should we do to make their life easier to convert over?
Hello. So I've been looking at doing this for ARM64, as I mentioned in the previous session. I think there are 2 or 3 major concerns that I have. One is that pre-return TIFF work loop. There are already ABI differences between architectures in how that works with respect to things like ptrace. I'm not entirely sure how we will abstract that in the generic code without effectively forcing much of the generic code back into architecture code. I don't have any specifics on that, just as a heads up that we're probably going to have to do something there.
The question is, why has this to be done differently on architectures?
Because it's ABI, unfortunately. It's not that it should have been. It's unfortunately, it's just the state of things. And going forwards, we definitely don't want to have this different across architectures. It just is at the moment.
Right. Yeah, we should look at that offline from this. I think we always have this problem when we create generic infrastructure after the fact that we then have to accommodate with historic ballast in the architectures.
Yeah.
That has been true for everything, timekeeping, generic interrupts or whatever. It's pretty much all the same thing all over the place. So you have to accommodate for the historic ballast.
Yeah, sure.
But
the other thing
that doesn't make the benefits less beneficial.
Oh no, I certainly think that we want to move to using the generic thing as soon as we can. I think for ARM64, my plan is to complete the migration of our assembly to architecture-specific C code, and then from there compare that against the generic C code and try and massage the two together.
Okay. Yeah, that makes sense.
Because we got a lot of bits like our pseudo NMI entry code, which is spread out across our entry assembly and some of our entry C code, and would have to fit somewhere between that and the generic C code, and it's not entirely clear what it would look like until we've got all of it in one place to begin with. I think the other thing that I've spotted is my understanding of the generic system call entry code that you've got is it assumes that all the context for the exception has been saved before you enter the generic faulting code. Whereas for ARM64, we end up saving that in series, like as we go through the entry path, up to the point where we become preemptible or interruptible. So I'm not sure how that would look on. I'm not sure how that will look for ARM64 eventually, because I don't want to have to go and save every potential piece of exception context up front, which might not be relevant for particular exceptions, because there's potential expense for doing that. But I also don't want to have hooks everywhere in the generic code in order to allow us to do that.
I mean, you need to have enough state established that you can call into the generic code.
Yes, so certainly before we can call anything instrumentable, we need to save all relevant exception state. The way we do this on ARM64 at the moment, we enter the kernel, we stash all the registers, we stash all the general purpose registers, we read a register which tells us which exception we've taken. We start calling certain bits of the context tracking code and that sort of thing, and then eventually get to the relevant handler for that specific exception, and then read additional state out of the CPU that's destroyed upon taking an exception. Reading all of those specific bits of state up front in a generic way is quite wasteful. So I prefer not to.
Yeah, but I don't think you need to. If your state is good enough to actually call into the generic entry code, and then the actual exception is after returning from doing that context tracking, locked app, or whatever needs to be done stuff, then you end up back in the architecture again to do whatever it's necessary to do for the particular exception. And if you have to save additional state, then it's fine.
Sure,
Look at the x86 page fault, for example. We do the generic exception entry stuff, and then we read our CR2 register, which says what the actual fault address was.
Oh, sure, but I'll need to double check that. But certainly when I looked at this a week or two ago, the generic entry code stuff did bits that would mean that on ARM64 we could potentially lose that context out of the CPU.
Okay.
I can't remember exactly what, but it meant that we could take certain exceptions at some point. So we might need to split that up into some early work, mid work, and late work, for example. I don't know exactly what would be.
Yeah, I mean, it's not cast in stone. I mean, if we have to split entry code up into 2 steps for accommodating ARM64, fine. We can still have the default be calling these 2 steps in one go for x86 or other architectures, and then ARM using a split variant of it. It shouldn't be rocket science to do that.
Yeah, I'm just raising that we're going to have to do something of that sort. And it sounds like Vinny is saying similar on ARC. So.
Anyone else?
Can you hear me?
Yeah.
Yeah, so I mean, similar story from us. I haven't looked as closely as Mark, but yeah, we've got most of ours in C now, so we'll just have to slowly go through and kind of work out where we need a arch hook or split something, or but yeah, I mean, I don't think there's any real showstoppers, but there probably will be. But yeah, we'll just chip away at it, I guess.
I mean, when I started working on that, I had a look across the architectures, and I mean, I probably missed tons of details how, especially all that assembly stuff works. But in general, the same stuff, like whatever it is, versus establishing state for RCU, locked app tracing, and whatever, and then the ptrace, seccomp, and TIFF stuff. It all looks so similar. I mean, there's always the devil in the details, but I don't think it's really fundamentally different on any architecture. So
yeah, I think
adding that extra bit to accommodate whatever special case power or ARM64 needs, I don't think it's going to be a problem.
Yep. Yeah, it's really just working out which differences are meaningful, or our C code and the generic is different, but some of it probably doesn't matter. Maybe a few bits are important. So yeah, but yep, we'll try and get it done before the next kernel summit or something.
Right.
Anybody else? More questions? Comments?
The one thing that I did spot that would be nice to have is we've obviously got that instrumentation begin, instrumentation end annotations, which are used by Objtool to check whether or not you're allowed to call instrumentation. It would be really nice if we could somehow track that at runtime, such that if you took an exception for a region you did not expect instrumentation on, we could give you a warning. For example, by looking in the backtrace to see if you're in an instrumentation function that came out of somewhere you shouldn't have been instrumented.
Interesting question. I put it on the think about it list. I don't know.
Yeah, because I reckon we've got.
One thing we could do is maybe extend the org information, because org can have unwind information per IP, and if part of that state is instrument enabled or disabled, we could maybe recreate it that way. But I'd have to find Josh and talk about that a bit. But that might be possible to do.
So I reckon we could just have a PercView variable and just store something into the PT regs in the early entry assembly, for example, just to keep track of it in a similar way to what we do for keeping track of our hardware PAN state on ARM64. And if we had that, you'd be able to say, I took an exception, I didn't have instrumentation enabled, I did not expect this, something is very wrong. And I note that we do have some warn-ons in bits of the entry code where we could take exceptions, which is a bit concerning.
Well, the thing is, if you trigger a warn-on, you're screwed anyway. So we excluded warn-on from instrument of the fact that we'll just try and get it out, but we're screwed.
I think at that point, I'd argue that's a sensible use case for a bug rather than a warn.
Well, someone hates bugs, and I mean there is a fair chance that you can maybe continue. Everything's out the window. Just try.
Yeah, there's some chance you survive, and that's what the hell. So there's some chance to survive. That's why we excluded bug from or warn-on from making object tool complain about validation violating the protection. Because you really, if you run in such a condition, you want to get that information out, no matter what. And maybe you survive, maybe not. Does that thing still work, or?
Yeah, I think we're waiting for the final sign that time's up.
No, we can move. If there are no more questions, we can move on, I think. And
yeah, shall we just start the next session, or shall we take a 3-minute break, 4-minute break?
I think we can start preparing for the next session until we upload the presentation and everything.
Okay.
It is going to be you and Linus.
Oh, that's right.
A 4G. Okay. Slide. Who do you want me to make a presenter? You do you take it yourself, or we transfer to Linus?
I'll just take it now.
Okay. So we have like 3 minutes before the schedule. I don't know if anybody was planning to join at exactly this the time. Maybe we'll wait another minute or two.
Yeah, let's wait 3 minutes.
Okay.
Mike, that's time for you to hand out snacks.
Transatlantic, yeah. Well, I was more thinking about having a beer session after the micro conference, if anybody wishes to join.
Yeah, I'm sorry the tea was cold and I ate the last chocolate chip cookie earlier.
Yeah, the hotel's awful. No one's done my bed.
Yeah, I also have to eat all the chocolate. That's right. Drew mentioned that. So I've eaten it all myself now this time. Yeah. Really big fingers, Linus. So shall we start? Maybe I can say a few words of introduction first. So this is something that started out from 2 observations. One observation was, like, there was a discussion earlier this year about HIMEM and whether we can already get rid of HIMEM support or if somebody's still using it. And the answer was yes, we are definitely still needing HIMEM for a couple of platforms. The other observation was that on 32-bit machines, mostly on ARM, memory, the available memory that had been growing over the years is actually getting smaller again as the high-end 32-bit machines that used to have more than 4 gigabytes are getting old. And the only available 32-bit machines tend to now be the slightly lower end, like Cortex A7s, usually with 1 or 2 gigabytes of RAM. So that there's actually a chance of removing high mem in the future. And if we can manage to fit the linear mapping into the kernel. And then a third thing that came up was an effort, there's actually a talk about this tomorrow, about kernel address space isolation for not mapping the linear mapping into the same page table as the user space for security purposes, like for preventing Spectre attacks and all that. And that's how we first started talking about this. And then we have one volunteer, Afzal Mohammed, who has actually started looking into implementing bits, and Linus has also started looking into this. And I'll hand over to Linus for some of the details about the implementation.
Yeah, do you all hear me well?
You're fine.
Yeah, so I'm not in presenter mode, so I can't really change the slides or anything. What we have, I have looked at Afzal's prototype, and this has been happening as, yeah, you know, just generically my attempt to understand things in general. So here are some sketches this morning, just so you get the general picture. The ARM architecture has traditionally this what we call the VM split. We split the virtual memory in a user space part, which is from 0 to C0 millions, and from C0 millions and to the top of the memory, that's where we map in the linear kernel space mappings. Give or take, the kernel space memory, the linear mapping there is also divided into what we call low mem and what we call the vmalloc space. So 768 megabytes is low mem and 256 megabytes is vmalloc. And by the way, there are people here who probably know this better than me, so you feel free to correct me. So this part down here, if you see my pointer, it's divided in, it's like cut around here. And that's, well, I can even draw here, I think. So this here is like, that's like low mem. Oh, this is silly. Like there's low mem, there's vmalloc above here. And the idea is to get rid of high mem. Like whenever we need to access high mem, we have to map it in here somewhere. We can't use user space, so we have to take some of this area and we have to pages. And that means like a lot of code around any use of high mem, and the predominant user of high mem is the page cache. And that's how the entire discussion started. So the idea is like, can we have it like that? Just one big, nice 4 gigabyte of map for kernel space, and then one for each user space process like that. And the idea is, we think we can do that. There will be a performance penalty. The performance penalty will sometimes be severe and make this probably impossible on some systems, but we should try. If we can just take these systems that have, say, over 4 gigs and convert it into something like this, like using a big stack of physical memory like this, and then from that we pick our kernel space allocations and user space allocations per process, etc., then everything would be shiny and great. The upside with this previous shared kernel mapping is, of course, that user space to kernel space can get pretty. You can make them much quicker since you don't have to map out this part of the page table. You can just keep these things around, and you don't replace this upper part. That's going to be, and that we have exploited. So Afzal has made a prototype that does this. One big physical memory, and I think he has tested this on the Versatile Express in QEMU, and he has also tested it on an OMAP platform. But I think that the actual OMAP or TI platform that is crucial here is going to be the Keystone. You can correct me if I'm wrong on this, but I think that's the mass-produced platform that's actually gonna be strongly affected by this.
Yes, so that's
the one we.
There's a couple of different platforms that are impacted differently. First of all, there are platforms that have more than 4 gigabytes, and this is the TI Keystone is the most important one. There's also one MIPS platform that has up to 8 gigabytes or even 16. And then we have a couple of 32-bit ARM server platforms that are completely obsolete by now, but they're still in use in some of the build farms that have not yet migrated to 64-bit machines.
I think sorry. I think it's another way of the high memory. I think it's another implementation of the high memory. That means the 8 gigabytes mapped this way. That means a lot of pages didn't covering in the direct mapping. Yeah.
Well, we would still use the traditional high mem. The only difference here is that we would have more low mem. So instead of having 3/4 of a gigabyte, we would have close to 4 gigabytes of low mem plus another 4 gigabytes of high mem, which also helps. Like having an extreme high mem ratio, like having much more high mem than low mem is generally a bad thing. Things start to misbehave if you try to do that. But the more interesting case in the long run would actually be the case where you have 4 gigabytes or less, but more than the 768 megabytes of RAM that we have in the typical low mem configuration.
Okay.
Because we can basically wait for the Keystone and the server platforms to die. It will be a couple of years. We don't know exactly how long, but it's clear that most of the other 32-bit ARM systems that are being used now are going to live longer than those. Because they are still being, like, you get new SoCs, and the Keystone is a couple of years old at this point.
Is that means the page table global bit could be deprecated, and we use one SID for the kernel space, such as SID 0 is for the kernel space area, and maybe it could be exchanged. I mean, it could be overflow from the SID cache. I mean, it should be constantly stay in the SID mechanism. I mean, SID is a window ID, and it needed to overflow and bring back. How about the kernel space memory address space SID mechanism? Yes.
Yeah, I'm sorry, I did not understand the question. Really.
I mean, every space have its own address space. That means they will cooperate with the SID address space identifying. Yeah. So I think a kernel space memory have his own SID,
Yes.
So how do you implement it? I mean, well, it will be a 0 SID. For example, we reserve the 0 SID for the kernel space, and we don't take care it because 0 won't be used by others. Yeah, and it will put for the kernel space. Or we treat the kernel space memory SID as the same with the other user space SID, and it could be catch out. And yeah, please.
I think I understand the question. So yes, I think for this to work properly, the minimum requirement would be that we have address space identifiers and reserve one for the linear mapping. Peter asked about this on x86, where Linus Torvalds hated the 4 gig split that we had outside of the kernel tree like 20 years ago. And at the time, x86 did not have address space identifiers, which made it incredibly expensive. My hope would be that we can do it on ARM, having it just rather expensive, but not incredibly expensive to do this. Because if you have to flush all the TLBs all the time, then the performance breaks down very quickly. But if you only have to do some tricks to access user space memory, then my hope is that we can make those tricks fast enough that it's acceptable for most use cases, and it outweighs the downsides of, it's not as bad as the downsides of HiMem that we already have at the moment.
Yeah, so all the copy from and copy to user will be very expensive.
We have a couple of ideas how to make it a little faster. So one thing that we can do on ARM is to have separate page tables for the high and the low bit, and have the VMLog area in one page table, and all of the linear memory and the user space in a different page table or set of page tables. So that if you have a get user call, you would only have to flip the page table, do the access, and flip it back. And we have to measure like how expensive this flipping of the page tables is, and the barrier that we get in there. So we have to flush the pipeline, but we don't have to flush any TLBs or change the page tables.
So you
like
have saying
change the
that you'd,
content.
am I correct in understanding that would effectively mean you're jumping into a trampoline which flips into the user space page tables, does the read, and then flips back into the kernel in order to do any get user, put user?
I don't think we actually have to have a trampoline. I think we can, in the inline get user version, we can flip the page tables, just do a flush the pipeline, access user space, and flush back before we.
Sure, but the code that needs to do that needs to be mapped, right? So
yes, and yes, okay. One thing that we haven't talked about is the idea at the moment would be to move the kernel VM Linux itself into the VMLog area, and have the VMLog area in the top page table.
Yeah.
It's a little trickier for copy to user, copy from user, because once we unmap the linear mapping, we lose access to the stack.
VMLog stack then.
Yeah, so we could map the stack using the equivalent of kmap or something like that, like fixmap. Or we could use all the available registers. So on 32-bit ARM, we can use an LDM to load 8 registers, so 32 bytes at once. So we could flip the page tables, load 8 bytes, flip them back, and save the 8 bytes, 8 registers, 32 bytes somewhere else. But once we get to more than 32 bytes of copy, then we need to flip the page tables more than once. And at that point, we might be better off doing some other trick. Like we could use neon registers, which is a whole other can of worms. But with neon registers, we can, I don't know how many is it, 256 bytes in total, something like that, that we can copy at once. doing one page table flip, or we could do the trick that the x86 4G patch had, where we walk the page tables and access the memory through the linear mapping.
I suspect the first thing to do is to benchmark copying, is to benchmark how expensive that flip is likely to be, because that's really going to be the thing that drives what you want to do next. And it's also worth noting that we can only do the 2 page table trick with LPAE kernels. Prior to LPAE, I think we only have 1 TTBR.
Yes, and I think that's fine on ARM. So the machines that actually need this, there's pretty much no machine out there that has more than 2 gigabytes and doesn't also support LPAE. The only one was the original high bank, which had a Cortex A9, and that supported close to 4 gigabytes. But we don't have to really worry about users on that one. So all the machine, I would think we should just do it for LPAE on ARM, and other architectures, if they want to copy this to RISC-V or MIPS or something, they might have different trade-offs. But that also makes it like, that simplifies the option space if we just do it for LPAE.
I think there are two problems to solve. One is mapping. I think mapping is not a big problem. And another problem is the data exchanges, such as the copy users, and you need to deal with the across the address space. And that is a very classic problem to the microkernel about the IPC. It's a huge problem. It's have we discussed many years ago, because microkernel cannot solve that problem. And this is microkernel design. If you can solve your problem, and a microkernel also could solve that. I think and a lot of hardware mechanism was mentioned and bring up to improve but that's not a successful and widely practiced hardware mechanism to do that. So how do you think about the exchange data for your proposal? I think it's need another hardware mechanism to help this.
We won't have another hardware mechanism, just because there won't be, like on ARM, there won't be any new 32-bit cores that actually need this, as far as I can tell. All the machines that need this are machines that have already been built. It looks like the largest configuration that anybody is going to do on 32-bit ARM machines is 2 gigabytes, and that's incredibly rare. The largest sensible configuration that we're going to see is 1 gigabyte. And for 1 gigabyte, we can just do the split slightly differently so that we can have a full gigabyte of low mem and slightly less user space memory, as we would do on a Cortex A9 without LPAE. And even for the 2 gigabyte configuration, we could just we could just do the split here in the middle. We could have 2 gigabytes of low mem, slightly less than 2 gigabytes of user space, and a little bit of VMalloc.
Oh, okay.
And I would suspect that's also the same for 32-bit RISC-V. And I have a whole section of my talk about architectures tomorrow about the fact that there's really no room for 32-bit machines with tons of memory anymore. If you have the 32-bit machine, you are not likely to have DDR4 memory. If you have DDR3 memory, the largest affordable configuration has half a gig of RAM per chip, and you're only going to have 1 or 2 chips, because if you're going higher than that, you end up with an expensive system, and if you have an expensive system, you should really have 64-bit at this point.
Do you have any slide, detailed slide to show how you implement the code exchange from the data from user space to kernel space. I mean, you have mentioned Oral for a Flash set up some temporary page mapping and copy them from.
I don't have any slides. I don't know, Linus, you didn't. You had one more slide, I think.
What exists today is this rough prototype that Afzal has made, and that's all. I mean, I haven't written any code in this regard. I just looked at something that somebody else did, and this is something that is hacked up, let's say. It boots, but it makes like a lot of assumptions about how, you have to have LPA, for example. Otherwise, and you destroy all systems that don't have it. We can't make code like that. So there is no real real implementation.
So if I understand correctly, you keep the kernel image mapped in both user and kernel. Is it the whole vmalloc space?
Yes. So we would use the TTBR1 register to have the top 256 megabytes of address space for the entire vmalloc area, and that would include the VM Linux. It would include the modules. It would include all dynamic allocations through vmalloc, and it would include things like fixmap. And
you can keep the stacks in the vmap stack.
I don't think having the stacks in the vmalloc area is going to work because it's not big enough for that. But we could think about that too.
Yeah. And
that would be an interesting idea to make it faster, because if we can just put something on the stack for copy to user, we could just loop around some.
I think it'd be worthwhile looking at that, because I know people were looking at vmap stack on ARM for security reasons in the past anyway. So it's something that we could implement completely orthogonally, get it upstream. And if it happens to benefit this, we could at that point know whether or not we have enough space in the vmark area. We could consider different sizes of the vmark area.
Yep.
And one thing for copy from user, I guess you could, what problem with, if you run in kernel space entirely, you'd have to do get user pages to map the page if you want to access the user page. But if you move to the actual user mapping, then you don't need the complications of get user pages, because you k-map the kernel page instead.
Right. It's just that if you unmap the linear mapping, you might not have any place to copy it to. Like if you can copy from user space, but you can't copy it to anywhere, because where the pointer that you're copying to might just not be on the stack. So if we use the stack, we would have to copy everything to the stack first, flip the page tables back, and then copy it to the final destination.
Oh, I meant you k-map the final destination in.
Right, that is the expensive implementation that we have already.
No, but you don't k-map. You k-map the kernel space while you run the user table.
Oh, yes, that also works.
Because you don't need. It's much cheaper, because the pages are there already. It's much cheaper than doing the get user pages to k-map.
Yes, absolutely. Yeah. Now, I think we hadn't discussed that yet on the list, but it's also an idea that I've had, and it's likely going to be faster, but we also have to measure that, I think.
And the kernel space, I think, is not all direct mapping. Maybe still needed to reserve some range to do some flexible mapping. Is that right?
Right. So yes, we've been talking ARM stuff for a bit. So to translate, the top 256 megabytes on ARM can sit in their own page table, and that would always be mapped, and that would always contain the kernel itself.
Okay. And okay, so what's the memory layout of the kernel space memory? I mean, have you some idea how to separate them in for the different function? I think that maybe there should be some function memory layout in the kernel space memory.
Yeah, so I think that's what Linus tried to show. We would have the 3.75 gigabytes of linear map for the low mem and 256 megabytes for everything else. And those everything else would always be mapped, and the linear map would not be executable. It would only be read-write.
Okay. Okay. So that's the, okay.
Yep, and we are pretty much out of time.
Hmm.
And
Yep. Good. So we have a next and the last break till the next round hour. Everybody is welcome to refresh their beverages, snacks, and everything. See you in a couple of minutes. Hello? Do you hear me?
Yes.
We do.
Okay. Uh, I think I cannot connect camera anymore. I'll try again. Okay, I think I have some troubles with this system. Um, do you see the slides? Because I don't.
I can see the first title page.
And do you mind taking the presenter and clicking next once in a while? Because somehow I lost the slides. Not sure it helps. Oh, shh.
So Mike, you see a little button that looks like a slideshow on the bottom right of your screen.
No, I see widescreen instead of the slide.
Yeah, that should restore the presentation. If you hover over it, it should say restore presentation.
Okay, so it shows if it shows a slide, that's then it's fine. I've just got some trouble with local set as well. Probably it's not the system, probably it's me. So I'm going to talk about when architecture meets memory management. There are several areas that kind of interface between memory management and the architecture. So there is still B management and MMU gather and so on that is being looked after and is very well maintained. There are pieces that related to lower level page table manipulations and the allocation of the page table memory. The third place where Arch interacts with the generic MM is the definition of memory models, not in the sense of memory ordering, but in the sense of discontinuous flat mem and sparse mem. And there is the very beginning of system life is memory detection and initialization. Now I'll start a bit with some bragging. It's a short quiz I did last year at Plumbers. So we have a PGD offset macro that takes an MM and a virtual address and returns pointer to the entry in the top level page table that maps that address. Linux supports 24 architectures. How many definitions of PGD offset do we need and how many do we have? And there is I always wanted to try a poll in the system. So there are answers on and please don't grab. Okay, so let's think. Yeah, majority is right. We had 31 until 5.a, and now we have two of them. One is generic for 23 architectures, and the 319 do some different things in this area. So we kind of had to retain their version. The next thing that can be done about page table manipulation, I'm still thinking if we would like to do it or not. It's mostly related to the page table folding. Although it's neat, it's nice, and now every architecture supports 5 levels of paging apparently. But we have a lot of empty conversions from the top level to the page table that is in reality top level, and many architectures support only 2 levels of the page tables. And once in couple of years, when Intel updates their hardware and everybody needs to update their architecture to introduce yet another level of page table, and it's not really nice. By the way, it's a feature that that was also implemented only for one architecture and never was completed for the others. So there are possible alternatives that is, for example, we can use page walk with callbacks, but it's slower than using loops of 5 levels of page table. We can think of a completely new interface. For instance, doing some like page table iterator that takes start end and does something. It also has a drawback because now with THP and the huge pages in different levels, it becomes quite different what each level does and how each level should be treated. Another thing that is worth doing in the area of page table manipulation is making headers like page.h and pagetable.h a bit less messy. x86 did some split by types and functions, and 32 versus 64. There is also something similar on ARM64, but in general it's very difficult to get through page.h and pagetable.h without breaking something. If you take one thing from there, you surely will break MM in the other. The next point is the memory models, and we still have 4 architectures that use discontinuous memory. It's Alpha, ARC, IA64, and M68K. We've been actively working with M68 people from time to time. I'm resurrecting the series of that replaces the discontinuous mem with sparse mem, but still we have some problems there. So for Alpha and IA64, I really don't know how to proceed. It's whenever I've sent several times patches to Alpha mailing list, surprisingly nobody actually responded. IA64 is a bit scary. It doesn't have simulator. I don't have access to the hardware, and it has some very weird dependencies of discontinuous mem on sparse mem, and probably as a very large instruction word architecture, they call vmemmap virtual memmap, so that it will fit into the paradigm. As for the ARC and IA64, M68K, for ARC there was a problem of mem map initialization for high mem, because high mem was lower than low mem. It was a very interesting decision we need. It was solved recently. Somewhere I heard, or probably I read one of the commit messages, that on arc sparse mem is less efficient than discontinuous mem, and there is a sparse mem causes either wasted memory map parts or large arrays of sections. The same is true for M68K, and for M68K, another complication is that it's hard to understand what are the actual possible hardware configurations, so that a section size can be picked up properly. So with sparse mem, for small architectures, let's say like ARC and M68K, we can increase the size. We either increase size of mem section array, or we need to decrease max fizz mem bits, because the room in page flags to store section address is limited to 8 bits, I think. It is possible to implement a virtual mem map for decreased overhead of the memory access for the PFN to virtual and virtual to PFN, but it will increase memory overhead. Or we can take ARM and ARM64 implementation of freeing memory map that is unused, and move it somewhere to more generic place, or even make sparse aware of architecture that can implement PFN valid and just allocate the section precisely to fit precisely into the actual populated memory. Arndt? We're going to say anything?
Oh, sorry, I was accidentally unmuted.
Oh, okay. And the next larger area of that begs for improvement is the memory initialization and the representation of physical memory banks. As of now, we have every architecture doing it its own unique way, and not only because obviously the firmware representation different, but the way from the firmware representation to the eventually running body allocator is different in all architectures, because each choose its own way of working around the problems with boot mem. Then when mem block first was introduced, the architectures like PowerPC and ARM used it extensively. x86 was slow on the transition, and it took a while with all the no mem block, no mem, boot mem, no boot mem, and wrappers around, and it's quite a big mess what we have there. I think the best example of memory initialization is actually mainframe S390. They have a very early reservation. They have memory detection, but I think they don't support complex memory topologies, which makes these things simpler. So it would be great if we could have some interface, say, between a third kernel and the architectures to have early reservation and memory detections that would happen even before setup arc. I'm not sure it's entirely possible, like Devil is in the details, but I think that after all architectures were converted to memblock, reading firmware memory map and translating it to memblock should be possible before as a full architecture setup is done.
I'm not sure that's sorry, Mike. I'm not sure that's quite true because some of the firmware detection stuff today happens in setup arch, and some of that can be dependent on the command line which setup arch parses in an architecture specific way.
Maybe you're right. But still, what I'd like to see, maybe we need something that setup arch can call into, or I don't know. Just as of now, it's all memory initialization is spread around setup arch. If you take a look at most of the, how did we call them, important architectures, it's all over the place. It would be better if it was at least concentrated somehow. Now another point is it would be nice to have memory detection together with NUMA configuration detection. Again, I'm not sure it's possible, maybe not. But what we do now is we do memblock add for the memory banks, and then after a while we do memblock set node for setting actual node information on the memory banks. And the last thing that also would be nice to have, in my view, is a unified representation of cold plug memory layout. I think we have memblock on ARM32, ARM64. We have memblock and the parts of device tree on PowerPC. We have E800, 820 on x86. Plus, we have some other construct on x86 that represents NUMA configuration of the memory. So unifying as much of that as possible seems useful and would simplify things and reduce the amount of code in each architecture. What I'm suggesting is to have the physical memory layout in memblock. Now, for most architectures, memblock is discarded and it lives in the init sections. So I think we can retain data and accessors for the memory and reserved probably configuration in the text and data section, and leave all the memblock allocator part in init and discard it during the boot. x86, there is an open question. I was wondering, x86 doesn't consider reserved memory a memory, which means it never adds it to memblock memory, and I think it's the only architecture that does it. So, and then looking at the logs, it was hop on, hop off. Somebody added these areas to memblock memory, somebody then removed them back, and then there is quite a lot of code in page allocator initializations that deals with the fact that reserved memory is not exactly memory, but it's some kind of weird memory. So another thing that I was thinking of doing is use memblock-based PFN valid for systems with sparse mem and few memory banks, and then we can make a sparse mem section size more precise and do not waste memory for memmap. So that's more or less all I had to say. Now I'm trying to see. If there are any questions, you're welcome to chime in.
Have you seen the? I have a question about how do you think about every architecture every architecture put up, and he must set up the early page mapping from the physical address change to the virtual address. Yeah, and the problem is we cannot get the exactly memory layout, physical memory layout from the DTB, but we needed to get some trampling map, and the RISC-V and ARM is the similar, and they have very similar code. If you see that code, you will see that's very similar. And do you have any idea to gathering there together, unify them together, and
what I meant is not unifying the memory detection. What I meant is that probably memory detection can run before setup Arch, and it can be called from start kernel or something like that. I'm not entirely sure it's possible. As Mark pointed out, there are dependencies in ARM64 that probably won't work this way.
So I think Gua's question was actually the way that we create the linear map on ARM64 and the way that RISC-V creates the linear map based on the DTB or ACPI tables or whatever. That's under Arch code and it looks very similar. And it probably could be factored out into generic code because we use fixed map slots to go and create the entire linear map page table, regardless of how much memory we have to begin with.
Yeah, I think somebody was working that recently, and I came to that conclusion as well.
Yeah, they look similar, but I think RISC-V has like two-stage mappings.
RISC-V history, implementation history, the first time he just one stage, and the second he changes to the two stage. Maybe Palmer is very familiar with that, and now the RISC-V early direct mapping, detect mapping before early mapping, it's the same with the ARM64. Yeah, that's it.
So the second stage is
I think we just need to clean it. Like, I think unifying the code with ARM64 will clean ours up. I just never really got around to it. So yeah,
it's always a problem.
Do you have a look at the Cisco early mapping? It's the simplest mapping of the all architectures.
I'm not sure it's the simplest of all architectures, but it's one of the simplest. Yes, I think Arc and architectures like probably smaller NIOS and NDS32 also have quite simple code.
It's always possible to do the simple thing when the problem space is not as wide, right?
Well, if you look at x86 or PowerPC, yeah. Well, I think I'm running out of time and nobody will show me that I am. So, last questions?
Yeah, I have a question.
Yeah.
So recently there's a patch, posted the patch for the ARM64 on basically moving the ARM64 NUMA code to common code so that RISC-V can use it. And that was simple because ARM64 was mostly written in generic way, so RISC-V could directly use that. but there are also suggestions about checking if x86 also can benefit that. Obviously, it's not trivial. There need to be code messaging, and then need to be more functional changes need to be introduced. But is that something that everybody is open to, that can be looked at?
We can look into it, but I'm not sure we'll succeed. Yeah.
Okay. Just wanted to know.
I didn't look. I didn't look into it myself. I can't say I know enough about how x86 and ARM64 do NUMA initialization to say okay, it's a good match or it's not very too far apart from each other.
Yeah, it's definitely not like it's not simple. That it might be
yeah, it might work out in the end, but I can't say for sure that it will.
Okay, but that is, at least it's worth looking into. That's what my question was.
I think so. Michael Ellerman, do you think PowerPC can be added as well? Michael probably is almost asleep. Anyway, thanks everybody for coming. Michael, are you here?
I'm asleep.
I see. 4 a.m. Okay, so I think we'll wrap up this presentation and let's switch to the default where we thank our sponsors. Thanks everybody for coming. I hope this microconf was not as boring and was useful for at least for anybody. And do you want to add something?
Here. Yeah, thank you everybody for joining. Thanks to all the presenters and thanks to all the sponsors. Yeah, on the break page I actually listed an extra slot in case there's any other topic that anybody wants to present. But I think we're all done. That's at least my impression from how people have been talking in the chat. And
actually, I had one thing I wanted to throw out just to see if anybody had any initial thoughts. We have these. We have basically these operations. Hold on a second. Let me just. If somebody else has something to say, let me just get my notes in shape. Give me one.
Paul, do you want a screen or something?
No, I don't have anything to present, just something to talk about, but it'll just give me, it'll just take a second for me to bring it up. Give me one moment. And if someone else has something to discuss in the meantime, please go ahead. Well, never mind. I think I'll just discuss this on the mailing lists.
Yeah, we have hack rooms. You can invite relevant people if you'd like to.
Mm-hmm. One more thing, maybe we can do a few minutes of feedback. Anything we should be doing differently if we do this again, or should we do it again next time? Let me just take a pause. Paul, custom Paul. No, wait, Paul. That's it. So should we do it again next time? Oh, I see an overwhelming number of yes. So far, 25 out of 73. 28.
I can
29.
vote as well. Oh.
Yes, I can't vote, but I can see who voted what.
Yeah.
Everybody voted yes so far. About half the people in the room have voted. Okay.
We eliminated one ARM32 machine, so it was worth it just in that.
That was totally worth it. And yes, let's just close the poll.
May I have a vote for my last approach, hardware approach mechanism?
Sure.
I listed that in. Okay. Can you bring up my presentation? I will talk about the last one. Yeah. Last slide. Yeah.
Okay. What was the name of the presentation?
Key probe, something.
The last hardware NICE hardware mechanism. That's shadow program counter.
Was it Linux Plumbers 2020 slides? Was it the
Linux Plumber? I think Key probe or something like that. I think.
That bring previous hardware is where. Okay, may I control this presentation?
Yes. There you go.
I want to get some feedback about the last proposal and welcome everybody. And I cannot control the slide. Okay. It's not so many slides. Moment.
Go is the presentation you've uploaded to the website.
Yeah. So much. I shouldn't. I shouldn't so much slide here. Yeah. It's about the shadow program counter, and I want you vote here. I will explain the principle again here, and how it works. That means this is a very simple implementation of the 5-stage pipeline you can find out in your school book, and it's based on the classical MIPS 5-stage. And this is program counter, and you can see program counter is the instruction fetch from the memory, and then OP code will be decoded here, and the another pace is the program counter's value will be input to here and to John the calculate, and the result such as branch, such as the value generate will be read back to the register, and some branch will read back to the PC, and the shadow. Okay. And the shadow program counter is put a shadow program counter near the PC, and when the program counter generated decode, but the value is not from the program counter; it's from the shadow program counter, and the value calculator is from the shadow program counter. And the benefit we could get is that if we put an instruction here, and we will set the shadow program counter, and then this value is stored at the PC relative address like this, and then this value will be set into the SPC, and the SPC have the value, and then it's enabled. The replaced instruction here, execution, is the same with the SPC value is. That means it will make the replace instructions execution behavior the same with the original instructions he has put. That will help a lot of instruction PC related instruction execute out of line in the same behavior. And then when any jump, make any jump or branch instructions back to the exception path, the SPC will disabled automatically. Yeah, and when the interrupts come in, and the SPC also will be saved in the PT rigs. That means we will change the PT rigs with the SPC, and in RISC-V we could use the CSR to set SPC and restore SPC and the time. So that is the mechanism of the hardware proposal. We call it it's the shadow program counter. And anybody have the opinion here? And I want give me the opinion. I will have a vote here. How, do you think it's valuable to implementation in the hardware? Okay. Oh, anybody have some feedback?
I suspect a lot of people have not been able to follow. And
yeah, I think this is probably the wrong place to discuss pipeline microarchitecture.
In fact, this instruction is designed for the key-probe. It's a key-probe optimized the specific hardware.
Yeah, I mean, and that's kind of the issue, is that it's very easy to tell that the instruction will implement what's necessary for software, and much harder to tell that it's a viable thing for real pipelines. We're not really that sort of venue, if that makes any sense.
Yeah, valuable. Well, I just mean I want to get answer. If no, okay, that's okay. Thanks, everybody.
You should talk to some more hardware designers, I think, because I suspect the ones I've talked to probably would not like that idea.
Pardon, Mitchell? What you say?
I think you should talk to some more hardware designers.
I have, in fact, this picture I have picked from the Google. In fact, that will a lot of complex picture about this. I just pick a simplest one, and I want to let you.
That's the problem, though.
Modern hardware is a bit more complex than this picture.
Yeah, the instruction decode will be like the 5th stage or something. Yeah,
and I just show you this. My proposal is very easy to implementation in the hardware. Very easy.
No, I don't think it is, but this is off topic.
I think we are a bit wandering off topic. Does anybody want to add something? More polls. More polls.
So I can actually found my notes and was curious to know if any of the other Arch maintainers on here, or for that matter anyone else, cares about atomic compare and exchange for anything less than a native word size.
You can run the poll. Let you.
How many of those do we have throughout the kernel tree at the moment, Paul?
Paul, you can run a poll.
Adam, you're already talking about something that's kind of beyond my ability here to do with.
You press a small plus, and there you can create a poll.
Okay. Here we go. I see now. Oops.
I was under the impression that the Q spin lock relied on that, for example.
On RISC-V, we haven't noticed too much that tries to use anything less than the native word size. And every now and then somebody writes a patch that tries to do like an exchange on a U8. And usually what happens is that if it's anything that's useful beyond their, specific device, it winds up breaking the build, and then they just promote it to a U32 or something, and that's it. But there's a bunch of nasty compatibility code in some of the architectures that tries to work around it with just lots of nasty code. And it occurred to me that one potentially sane way to handle this would be to just get rid of all that compatibility code for all architectures and just say, okay, if you want to do this exchange, run an exchange, you want to do it on a native word size
So I'm
value.
pretty sure that there are cases where some architectures will absolutely want to do it on a sub-word type. I was quite sure that the QSpinlock did that in some cases. I thought it did it on a single byte at one point, but that might be an older version of it, not the version that's currently in mainline.
Okay, thanks for the pointer. I'll take a look at the QSpinlock stuff. That's going to be a problem for at least some architectures that don't have fast native support for that, of which there are quite a few, as it turns out. So.
The end result might just be this needs to be an Arch has whatever flag for that, and if you don't have it, you don't get the features that rely on it.
Let's see if I can start a poll. Oops, okay. Waiting for responses, but how do I put in a question? I guess so.
Just ask the question, and if it's
Okay.
a yes no question, just ask it.
Yeah, do other folks care about sub-native word size exchanges? I should have had like 3 options: yes, no, or don't care. Okay,
So
it looks like 2 people said yes and 3 people said no.
So apparently, majority is for no.
Okay, thanks, guys.
Okay, I see Helge said, Paul, I agree. I presume it was to the sub word size for compare exchange.
Yes, it was. I
Yeah,
fully
so,
agree that it should be limited to.
so pay risk is interested, Paul.
Well,
Okay, great.
We don't have any compare and exchange instructions at all. So we have to do it with a single hash table. We can do any size you want with that.
Pay risk is half interested.
I'm saying we don't have any architectural constraints because we can't do compare exchange.
Well, RISC-V doesn't have compare exchange either, but that doesn't mean that we don't have code that implements atomic exchange. So,
just as a matter of curiosity, what do you do? Because we basically use a bank of hash spin locks to do the compare and exchange.
We have load reserve stir conditional, so we just do it, if that makes sense.
yeah, usually, there are usually those 2, general approaches. Either you've got, well, I guess there's a third, which is if you don't have, load reserved and store conditional, nor an instruction. But if you look at if folks are curious about this, definitely look at some of the nasty compatibility code that's in there for some of the architectures for exchange. It's pretty horrible for something that's probably intended to be high performance.
It is. It was designed by x86 to be high performance. That's why it caused us so much pain.
All right, thanks everybody.
Welcome.
It looks like a lot of people have already left, so I think we should just close it then.
Just don't press end session button.
Button. Yeah.
Oh, Giri moved it. Okay. I
No,
think you did. Okay. So I think everyone can stay, and I don't know. We have enough moderators anyway to keep the room running, and I don't know what is the timeout now.
The room will time out as soon as the last person leaves.
Okay. Vincenzo?
Hey.
Yeah, now we hear you.
Okay. Yeah, sorry. I got unmuted unwillingly.
Okay.
Yeah, I wasn't trying to talk.
No problem.
Anyway, is the session finished, or are we expecting for anything else?
There are 41 people online, and they probably until the last person leaves, the session is not completely finished.
We just assume it's turned into a hack room now. So anybody, please just turn on your camera so we can all wave to each other and have some fun.
I think not everybody has a camera. Somebody
Whoever has a
complained.
camera, yeah.
Anyway, thanks for having me. It was a great experience. My first at the micro conference.
You're welcome. Like only three people have cameras.
Wow.
I think that the other people just forgot to close their client.
Yeah, everybody.
People probably left a long time ago, but
yeah.
Why not all people take on the camera? Maybe we have a screenshot.
We'll surely have it's all recorded and replayed on YouTube at the moment we speak.
Yeah, maybe some people have a camera but no pants.
Well, it shows only this. It doesn't matter about do you have pants or no. And aren't you had a jacket a while ago? So.
Yeah, that was only for my presentation.
And surprise from James, no bow ties this time.
Okay, my bad.
Well, I have to unmute the audio as well. I actually have an emergency brochure that Federico Lucifredi got me. It's in a little tin, but it's in the bathroom. I have to go get it. It's a tip-on.
Well, hopefully we'll be able to meet up next year anyway.
Yep.
You do realize that if this crashes the infrastructure, John Corbett is going to be after you.
Well, apparently, if we pass 40 people with the camera on, should crash the infrastructure. So.
James, how many people with camera on maximum you tested?
I think we got it to about 100.
No,
so you don't have enough.
So we have a room to grow.
Okay.
Pretty much, yeah. But just remember, every camera on increases our bandwidth of the server by 5 times the number of attendees megabits. And we're on a plan where we pay per megabit, and it's all on my credit card. So right at the moment, it's costing me a lot of money.
But this time you don't need to bother with the top shelf in the bar.
Oh, well, actually, we could have a showing of the whiskey collection, yeah.
There's only 34 people left in the stream, so it's multiplayer is not that huge.
Yeah, the problem with the whiskey collection is this conference is the wrong time for me. It's just about to be 11 a.m. here, and I have to do other meetings.
Oh, for us, it's okay.
Yeah. Yeah, it's end of the day, so.
But this is pretty much the grave disadvantage of virtual conferences. You're not on the time zone that everybody else is on. And you're not officially off work.
Yeah. In a sense.
All right. Well, I'm off. Gotta go to dinner. Good to see y'all.
Bye, Grant.
Bye bye. I've got a service reboot to annoy Guy. Bye, Guy.
Yeah, I think I'm leaving as well. See you tomorrow, guys.
Bye. See you tomorrow.
Does anybody copy the shared notes into somewhere that
I did a while ago, and I think we still need to fill up more notes. I copied the notes and I copied the chat.
I'm off to then.
Well, I think I'm also going to get off. Okay, so thanks everybody for coming. Goodbye.